There's just a few more reactions that we need to cover when it comes to alkynes. So if you recall, when we're dealing with double bonds and we add an X2, we basically go through a halonium intermediate, and so the other X minus, whatever that may be, will come in from the anti position. So that would be an anti-addition of a product. For these same type of reasons, when we have an alkyne, we end up adding one equivalent of X2. When we do that, it goes to a trans type of product here. If you continue and have excess or two equivalents of X2, where that be Cl2 or Br2, then we can end up having four of those halogens left there, okay? In also a similar way, when we have ozonolysis that takes place, remember when we have a double bond, we end up chopping this bond right here, and that gives us an oxygen that's left behind. I kind of like to think of this as fancy scissors that leave those intricate designs. If you go through ozonolysis, what you're doing is you're cutting that there and you're leaving behind the fanciness of extra oxygens. Here we're just using O3 and then a mild reducing reagent of DMS or zinc. So when it comes to using a triple bond, we don't have to use DMS or zinc. We can just use water. And in this case, we have more bonds to chop. So there's more oxygens that are left behind. So instead of just leaving you with two aldehydes, you're actually left with two carboxylic acids. So it makes those occur on both sides. If you have a terminal alkyne, so a hydrogen would be right here, then what we actually see is as you chop that off, you end up with two C double bond O's to that same carbon. So that's just what you get. CO2 will bubble out. Okay. And lastly, it's really important when it comes to using what we sort of looked at last time. And that is when we have terminal alkynes, we can make a great nucleophile out of them simply by adding NaNH2. So this is this strong base that will then make a negative charge on that terminal alkyne, because what it's doing is it's ripping off the hydrogen that's there. If you then add an alkyl halide or something with a good leaving group, what that effectively does is it allows the negative charge that's built up here, so right there, to come in and kick out that X, whatever that leaving group is, and you get the R group attached to that triple bond. Then you can do a whole host of other things. And let's say that we're even starting with just acetylene, so that would be your triple bond by itself. First, you would end up making that negative charge because we have a strong base here in NaNH2. And so then we could kick out that leaving group. And then, since we still have a hydrogen here, we could remove the other side. So this comes off, and what we would end up having would be a negative charge that can then react a second time, and X leaves. And so you end up with an R group on both sides. Those can be different R groups, or they can be the same, just depending on what you want there. And this means that it's a very powerful tool when it comes to synthesis, because from that point, you can do a whole host of other things that we talked about. You can make two carboxylic acids with ozonolysis. You can end up making ketones. You can end up adding large amounts of bromine or chlorine or whatever it is that you want to make. So there's a wide variety of things that you can do here. You could end up with trans or cis alkenes with different R groups on it. There's a whole host of things that you can do. And that is very, very important when it comes to synthesis, which is going to be our next favorite topic. And I hope that you enjoy it as much as I do. Thank you.